Hello there. Quick recap before we get into our notes for today. Last week you worked really hard on number system standards 1 and 2, just so that you're aware of what the state course says you're supposed to learn and what we, Miss Johnson and I, are teaching you. It matches it. Okay, so we're in the number system strand. You just finished up number system standard 1, which is all about this stuff, right? Rational versus irrational. Rational being terminating, repeating decimals, or anything that can be written in the form a over b, where a and b are integers, because that absolutely includes your terminating and repeating decimals. Versus irrational, which is numbers like pi or square rooting non-perfect squares. What they turn into are non-terminating, non-repeating decimals. So that was standard 1. You guys worked on that. You also worked on standard 2, which was all about just recognizing that everything in the real number system, whether rational or irrational, has an equivalent form, something else you can write it in. Some of them are exact forms, like the rational. For irrational, we were getting decimal approximations. And actually what we're going to learn next, starting right now, is we are going to learn about how you can actually take some of those irrational values with square roots on them, and you can still write them a different way that's not even a decimal approximation. Okay, so that's what we're gonna learn starting now. So everybody get out page 8, get that in front of you, and let's get started. To start off, let's focus on the title of this page and make sure we're getting all of the vocabulary behind this, because you'll see this word come up this year and you'll see it again actually in 10th grade as you work through a class called Secondary Math 2. Over here in the title, it says simplifying radical expressions. You've perhaps heard that word, I don't know, in Teenage Mutant Ninja Turtles or something. It is actually a math word that has meaning. So I just took my pen and I circled it, and I would like you to do the same, because we're actually going to come down here. We're going to draw an arrow down here to tell ourselves that this actually has mathematical meaning. It's not actually, its mathematical meaning has nothing to do with the way that Michelangelo says it in the Teenage Mutant Ninja Turtles. So down here, in the English language, and this applies to any subject area you're working in the English language, we often have a different word for the noun version of something versus the verb. Remember, a noun is a thing, an item, and a verb is an action, right? So this symbol right here, we've seen it. We've used it. I'm going to draw nice and big. It actually technically has a little thing like that too. We just don't always draw that. We know this symbol. This symbol is a square root symbol. The thing I want to clarify right now is that square root is actually, and I'm just going to change colors here. I'm going to say square root is actually the verb. Okay, square root is the verb for this symbol. When we say square root, we're saying that's the action that you should take. That's the mathematical action. It's you are actually square rooting something. It's a verb. It's an action. It's what you do. Okay, when we say radical, we are now actually talking about just the name of the symbol. So a radical is a noun. Two different words because it's describing two different parts of this. When you say square root, you're actually talking about the verb, the action, that's what you're doing. So when you see that symbol mathematically, you're supposed to do something, you're supposed to square root it. But what you can just call the symbol is a radical. So this page of notes is all about how to simplify. Now we've heard that word in mathematics before too. We do that with lots of things. We do that with fractions, like 4/8 is 1/2, that's called simplifying. We do it with expressions, like 3x plus 2x equals 5x, that's called simplifying as well. It's when you take something in a certain form and you create an equivalent form out of it. It looks different, but it's actually the same mathematical value. We are going to learn how to do that with radicals. We totally know how to type them in a calculator and get a decimal. That is not what we're doing today. We are not actually going to get any decimals today beyond just to verify that what we did makes mathematical sense. So let's take it back to a visual for just a second. Let's come over here. Take your brain back to that first week where you got to work with squares, and I know you loved it and had so much fun with those squares. Some of you that's true for, some of you it's not. It's okay, I'm gonna take you through this. This says determine the length of each line segment without using a ruler. So, and a ruler might not help very much anyway right now because we don't want centimeters or whatever. We want to measure the line segment in terms of the dots on the paper. Okay, now the way that we did this the first week of school, I'm going to refresh your memories here. If I want to know the length of line segment A, one of the things that I can do right now is turn that into a square. And I'm going to use pink to turn this line segment A into the side length of a square. Remember, the way that we did that is we just went to this diagonal here, and then finished it off here. And we worked with this square quite a bit in the first week of school. Remember, we found the area of this square. Remember, it was half and half and all that. Remember, the area of this square was 2, which means the side length, I'm going to write it over here, the side length was square root of 2. Okay, that's actually just going to start us off here. I could absolutely turn that into a decimal. We can get a decimal approximation for it, and I will just because I know a lot of you want to. I'm going to type in square root of 2 in my calculator, and I'm going to write it like this. This is approximately, and you worked on this in standard 2, 1.41. That's the approximate length. This is the exact length. And let's just label that for ourselves so that we know what we're talking about here. This is called exact form with the radical still on it. Okay, so this still has the radical on it. At that point, when that radical symbol is on it, you haven't actually taken the action yet. You haven't done the square root, that's why it's still written there. As soon as you take that action and do that verb, now you have a decimal approximation. Okay, so exact form is nice because I know this is just an approximation and I can't even write this entire decimal because I know it's not over. My calculator just ran out of room. But a decimal approximation ends up being really nice in real life calculations when you're trying to work with it. But exact form is super useful as well and oftentimes easier to write. So again, exact form still has the radical on it. And decimal approximation is actually after you've applied the square root and actually done the verb. Okay, now watch what happens here. For B, I'm going to use a different color because I want to show you something. So if I turn this into the side length of a square, I know I drew these squares in the first week of school, but I can see this goes across 2 diagonals. So here we go, draw this with me. This is going to go across 2 diagonals. I'm going to come down here and draw it across 2 diagonals. You with me still? And then I'm going to come across these 2 diagonals. Now, what we did in class is we found the area of that whole thing and then we square rooted it. I want to show you something a little bit different here. I can also see, well, actually, you know what? I'm going to do that. Do you remember how you can turn this into 2 or 4 big triangles? Remember that? And this is 2 by 2, which would be 4, which means this is 2, 4, 6, 8. So the area of this whole thing is 8. You okay with that? The area of that is 8, which means the side length is 8. I'm going to start by writing this down here. I'm not going to write it up here. I'm going to show you why. I'm going to start by writing square root of 8. Okay? But I need to show you something. This actually has another exact form that I could change it to. Okay, it has another exact form that I could change this to. Here, if I come back up here, watch what happens. If I draw, see that original pink square right there? That is the same size as that pink square right there. And I could draw another one right here. And I could totally draw more over here. But I am only worried about this side length right here. So what happens here is I can look at this, there's a fly in here. I can look at this kind of like a ruler with scale markings on it. So this would be like 0, right? I know how big this piece is. It matches this pink piece right here. So this is square root of 2. It's one of them. I'm going to put a 1 in front of it. So this is like 1 square root of 2. And isn't this distance right here just another square root of 2? So this distance here is actually 2 square root of 2. That's how we say that out loud. I'll say that again. If I'm counting by square root of 2, this is 0, 1 square root of 2, 2 square root of 2. And you know what that tells me? That tells me that square root of 8 is actually exactly the same as 2 square root of 2. What? Why? I'm gonna let you think on that for a minute, and we'll see if we can figure it out. While you're thinking on that, let's move on to the next one and see if you have a theory as to why that's happening, see if it applies as we continue. This one, line segment C, goes 1, 2, 3 diagonals. So here I go. I'm gonna go 1, 2, 3, draw that. 1, 2, 3, draw that. And then connect these. Okay, if I find the area of this, here's my triangles. They're 3 by 3, which is 9, which means each of these is 4.5, 4.5. So there's 9 again there and 9 again there. Hey, this whole thing is 18, which means the side length, there's this little fly, which means the side length here is square root of 18. But also, let's think of it like our little number line. Look, this little pink square follows right along here too. Check this out. This time, how many pink squares is it to get across this distance? 3 of them. Huh, watch. Okay, so this is 0. This is 1 square root of 2. Label these with me on your picture. This is 2 square root of 2. And of course, this would be 3 square root of 2. I'm just counting by square roots of 2 because that's how long these break into. It breaks into that same distance as A. So square root of 18 is actually the same as 3 square root of 2? What? Okay, I actually can't draw this last one. I mean, I can't quite fit it all. I can go like this, 1, 2, 3, 4, and I can imagine what it's gonna look like. So I'm gonna tell you that the area of that one overall would be 32, which means the side length would be square root of 32. Can you guess what that's going to equal? Well, I'm gonna have 1, 2, 3, 4 markings on this. So this is going to equal 4 square root of 2. Okay, why is that happening? First of all, this one right here really is 1 square root of 2. Remember in math, you can always, if it's right next to the radical like that, it means multiplication. And so we can just assume, I mean, 1 times square root of 2. Remember, you can write x or 1x, and you can just assume the 1 is there. You don't have to write it. Same exact idea here. So this first distance was 1 square root of 2. So all we could do is make a decimal approximation. That's the best you can do with exact form. When it was square root of 8, that turned into 2 square root of 2. Square root of 18 turned into 3 square root of 2. And square root of 32 turned into 4 square root of 2. Why? Think on that for a second. I want to take your brain back to something really important. Let's come over here and let's tell ourselves something. Let's give ourselves an excellent reminder of a really important list. Here we go, I'm writing it over here. As you work over the next couple of days, I find it very useful to have this list in my brain, this list of perfect squares. Perfect squares come from squaring whole numbers. 1 squared is 1, so 1's a perfect square. I'm going to tell you right now that's probably the least useful perfect square, but it is a perfect square. 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared, 6 squared, 7 squared, 8 squared, 9 squared, 10 squared. I like to go, I got a little dyslexic there, 121, not 1, 1, 2, 1. That's 11 squared, 121. 144. Up to 12 is usually a good amount to have memorized in your brain, but you can easily figure out beyond that, right? Okay, perfect squares. Now, why do I bring those up? Well, I'll come back up here for a moment. Watch this. 8 is the same as 4 times 2? 18 is the same as 9 times 2. And guess what? 32 is the same as 16 times 2. Look at these brilliant, beautiful, magical numbers right here. Do you see what they are? They're perfect squares. When it comes to simplifying a radical, because you're dealing with square roots, if you can find perfect squares in there, you can square root that part without getting a crazy decimal, and then you just leave the rest inside. And if you're looking at that and you're like, I'm not sure I'm following Miss McGowan, that is okay. Stay with me, okay? For example, down here, if you try to use that similar thinking, okay, I'm going to start with this one. This is a different tilt. It goes down 1 over 3. Do you remember that? So I'm actually going to twist my paper, and I'm going to go down 1 over 3. And I'm going to connect that right here. Okay, got that one? Then I'm going to twist upside down, and I'm going to go down 1 over 3. And then I'm going to twist to the side, and I'm going to say, oh, just finish that up. Now, this is one that we calculated the area of, and I can show you real quick, but it's where we just drew this. Truly, that's not the main idea of these notes today, so you can just kind of quickly draw this and remember. But this is 1.5, 1.5, 1.5, 1.5, so 3, 6, 7, 8, 9, 10. The area of this square is 10. Which means the side length right here is square root of 10. Okay, we could get a decimal approximation for that. That's the best we could do. Otherwise, that is completely simplified. So this is approximately 3.16. Now here's the deal, okay? Can you see this down 1 over 3 movement? This line segment F is doing E twice. So watch, if I just count, this is 0. This is 1 square root of 10, and this is 2 square root of 10. And I'm going to tell you right now that if I drew that whole big square out, it would go 10, 20, 30, 40. So watch this. Square root of 40 is the same as 2 square root of 10. This is what we're going to work on now, and the visuals really help you see why this is going on and what's happening. But if it makes you feel any better right now, we're actually going to try and just figure out how we can not have to do this and how we can go straight from this to this. Okay, so we're going to focus on some of the algebra behind this. And I want you to understand, in case you're like, wait, there's no way that's really the same. Like right here, how could that possibly be the same? Let's just verify it really quickly on this next part. It says, consider the radical expressions given. Radical expressions, they are called radical expressions because they have the radical symbol in it. That's the noun. It does, in fact, mean to square root, but the noun version is called a radical. So it says, let's find a decimal approximation just so that we verify in our brains something here. So I'm going to type in my calculator, square root of 32. Now I'm actually doing the verb, the action, square rooting. Okay, so the square root of 32, I'm going to put this, square root of 32 is approximately 5.66 because it says 656. The next number is a 6, bump it up. Okay, now this one right here, find a decimal approximation for 4 square root of 2. And this you reviewed with Miss Johnson last week. This means multiply. So you do square root of 2 first and then times by 4. Actually, if you have a calculator like this, you can just type it in like this, 4 square root 2, and it will just automatically, it'll do the order of operations correctly. It'll square it first and then it'll multiply. Would you look at that? 4 square root of 2 is approximately 5.66. Okay, this verifies for me that these two are in fact the same mathematical value. We are going to now, without a picture, without squares, without dot paper, we're now going to try and verify in 2 different ways that those are in fact equal to each other. And by the end of today's notes, you do not have to be experts at this. We're going to practice this a lot over the next couple of days. So Don't panic if you don't fully get it yet. Just stay with me, okay? There are two main processes that we use to do this. One of them is called largest perfect square. I love this method. I love both methods. I love this method if I can keep my perfect squares in my brain, then it works really well, okay? Largest perfect square means what is the biggest one of these that is a factor of 32, okay? So, for example, 1 goes into 32, but is that the largest perfect square that goes into it? 4 goes into 32, but is that the largest? 9 doesn't go into it. 16 goes into 32. So here's what I'm going to do. I'm going to rewrite square root of 32 as I'm putting the radical symbol. I'm writing the radical symbol because I have not used it yet. I haven't actually done the square rooting verb. I haven't done that. All I'm doing is factoring 32. So I'm going to write the square root symbol because I haven't used it. 32 is 16 times 2. I haven't square rooted anything. All I've done is factor. I'm going to say that again. I haven't square rooted anything. All I've done is factor. That is why I still have to write the radical. Now, this is my perfect square. Now I'm actually going to do the verb part. I'm going to square root it, but I'm only going to do it with the part that works out nicely, the square root part. What is the square root of 16? It's 4. Did I square root this part? No, I did not, because that would have given me a long, crazy decimal, and I didn't want that. So guess what? I didn't square root that part. That part still has the radical. Therefore, square root of 32 changes into square root of 16 times 2, which changes into 4 square root of 2. Largest perfect square method. Excellent method. We're going to practice it a lot over the next couple of days. One more method that's really, really, really useful is called the factor tree method. What in the world is a factor tree? That is an elementary thing that you guys did. Here's what you do with the factor tree method. Take the number that is inside the radical, 32, and factor it out using whatever factors you want. The reason this method is nice is you don't have to remember what perfect squares are or not. You can just factor however you want. So if you look at this and you go, okay, the first thing that comes to my mind is 8 times 4. Remember, this is a factor tree. 8 times 4. Great. Am I done? No. Because 8 is 4 times 2, and 4 is 2 times 2. Am I done yet? No, because 4 is 2 times 2. Okay, once you hit this point, remember the ends of your tree, that's where all of your what we call prime factorization is. Now I'm going to put the radical back there. I'm going to say, okay, I haven't actually square rooted anything. All I did was factor stuff. Again, I have not square rooted. All I did was factor. The verb that I did here, factor. And I got 1, 2, 3, 4, 5 2s. And here's a handy little trick again that we'll practice over the next couple of days. You can now, instead of trying to find the largest perfect square, you can do this. For every 2, take out 1. And I don't mean the number 2, I mean for every pair, okay? For every pair of factors, take out 1. So I've got a pair there and I've got a pair there. So I'm going to take out a 2 for this pair. I'm going to take out a 2 for this pair. And they were factors, so they're still going to be multiplied. Does this one have a pair? No, that's just a single 2 guy. That guy has to stay inside the radical. And watch if I clean this up. 2 times 2 is 4, square root of 2. Okay, we are going to practice both of those methods, and you'll get to choose whichever method makes more sense to you. That'll be the one that you'll use a lot. Doesn't matter to me. You're going to practice actually this idea and finding largest perfect squares, so you don't fully have to go through this process just yet. Keep in mind we're going to practice it a lot over the next couple of days. Give your math practice some try today. Give it a try, and then we'll do some more simplifying tomorrow.